Hi, this is Nancy Wei, and the topic of my final project is Cloudera Impala. In the recent decade, with the expansion of users on the mobile web, there has been an explosion of the amount of data available to businesses and government agencies. To gain insight into these massive amounts of data, also known as big data, researchers have developed new ways to represent entities and its attributes in more flexible, scalable distributed file systems. In 2010, Google published a paper on Dremel, a scalable, interactive, ad hoc query system for the analysis of read-only nested data. This system interested many businesses who wanted to perform large-scale data analysis without dealing with the traditional but inflexible relational database management system. While an RDBMS is great for analyzing transactions, for example, data related to static attributes such as financial data, ERP, and log messages, it is not ideal for analyzing data consisting of complex entities with evolving data attributes. For example, website visitor data and marketing data is so dynamic and hierarchical that an RDBMS would be too inflexible to use for modeling and querying this type of data. Since Apache Hadoop was introduced in 2005 and Hive in 2009, businesses wanted to incorporate the power of MapReduce-based computing into data analytics while sticking with the relational models that they have been working with decades before. As businesses increasingly rely on large-scale data drawn from multiple sources, often in real time, they need a way to analyze the data efficiently by housing it in a distributed file system like HDFS, while being able to query, join, and perform other advanced data analytics operations to make use of evolving streaming data. This business problem inspired Google Research Labs to create Dremel. By combining multi-level execution trees in column-like data layout, it is capable of running aggregation queries over a trillion-row table in seconds. The Dremel system scales to thousands of CPUs and petabytes of data. Furthermore, Dremel complements MapReduce-based computing. It is a novel columnar storage representation for nested records. Google was able to demonstrate its benefit by performing further experiments on a few thousand node instances. Based on the Dremel paper, researchers at Cloudera created Impala, an open-source code base which allows users to query data in real time. The data may also be stored in HDFS or Apache HBase. Impala's system allows businesses to bring real-time and ad hoc query capability to Apache Hadoop and complements traditional MapReduce batch processing. Users can query data stored in HDFS or Apache HBase using familiar SQL-like commands, including select, join, and aggregate functions. Such queries can be performed in real time. Furthermore, Impala uses the same metadata, Hive SQL syntax, ODBC driver, and user interface such as Hue Beeswax as Apache Hive. This provides a familiar and unified platform for batch-oriented or real-time queries. Businesses using Impala can implement a MapReduce-based querying system with little setup overhead. To avoid latency, Impala circumvents MapReduce to directly access the data through a specialized distributed query engine that is very familiar to those found in commercial parallel relational database management systems. Cloudera claims Impala can perform faster than Hive, depending on the type of query and configuration. There are many advantages to Cloudera's approach over alternative approaches for querying Hadoop data. First, local processing is performed on data nodes, so network bottlenecks are avoided. Second, a single open and unified metadata store can be utilized. Also, costly data format conversion is unnecessary and thus no overhead is incurred. All data is immediately queryable with no delay for extract, transform, and load type jobs. All hardware is utilized for Impala queries as well as for MapReduce. Furthermore, only a single machine pool is needed to scale. This single system for big data processing and analytics allows businesses to avoid costly modeling and ETL just for analytics. Impala is 100% open source with an Apache license, whereas Dremel is proprietary to Google. When comparing Impala queries with Hive queries, performance is dependent on several factors. Number 1, hardware configuration. Impala is generally able to take full advantage of hardware resources and specifically generates less CPU load than Hive, which often translates to higher observed aggregate I/O bandwidth than with Hive. Impala, of course, cannot go faster than the hardware permits, so any hardware bottlenecks will limit the observed speedup. For purely I/O-bound queries, Cloudera claims performance improvement in the range of 3 to 4 times. The second factor is complexity of the query. Queries that require multiple MapReduce phases in Hive or require reduced side joins will see a higher speedup than, say, simple single table aggregation queries. For queries with at least one join, Cloudera claims that its system has performance gains of 7 to 45 times. The third factor is the availability of main memory as a cache for table data. If the data accessed through the query comes out of the cache, the speedup will be more dramatic, and Cloudera claims that Impala improves performance by speeds of up to 20 to 90 times over Hive, even on simple aggregation queries. Given these key benefits, Impala is not a replacement for MapReduce, Apache Hive, nor a traditional data warehouse infrastructure. There will continue to be many viable use cases for MapReduce and Hive, for example, for long-running data transformation workloads, as well as traditional data warehouse frameworks. For example, for complex analytics on limited structured datasets. Impala is a complement to these approaches, supporting use cases where users need to interact with very large datasets across all data silos to get focused result sets quickly. There are some limitations to Impala, which is currently in its beta release. According to Cloudera, supported file formats in the first beta drop include text files and sequence files, with many other formats to be supported in the upcoming production release. Currently, all joins are done in a memory space no larger than that of the smallest node in the cluster. In production, joins will be done in aggregate memory. Lastly, no UDFs are possible at this time. Impala is an addition to tools available for querying big data. Impala does not replace the batch processing frameworks built on MapReduce such as Hive. For long-running batch jobs such as those involving batch processing of extract, transform, and load type jobs, Hive and other frameworks built on MapReduce are still best suited. Let's discuss the primary features of Impala. It provides support for most common SQL 92 features of Hive's standard query language, including select, joins, and aggregate functions. HDFS and HBase storage, starting with HDFS file formats, text file, sequence file, RC file, Avro file, and Parquet. Compression codecs such as Snappy, gzip, deflate, bzip. Common Hive interfaces including JDBC driver, ODBC driver, QBeeswax, and Impala command line interface. Now let's take a look at how Impala fits in with the Cloudera environment. The boxes you see in orange are Impala's components. The boxes in blue are all the other components that Impala is able to work with. First, let's look at how each component of Impala using 3 nodes. We have the Impala state store, which checks on the health of Impala daemons on all the other nodes in a cluster. We have the Impala state store, which checks on the health of Impala daemons on all the nodes in a cluster and continuously relays its findings to each of those daemons. It is physically represented by a daemon process named state stored. Only one of such process on one node in the cluster is needed. If an Impala node goes offline due to hardware failure, network error, software issues, or other reasons, the state store informs all the other nodes so that future queries can avoid making requests to the unreachable node. Because the state store's purpose is to help when things go wrong, it is not critical to the normal operation of an Impala cluster. If the state store is not running or becomes unreachable, the other nodes continue running and distributing work among themselves as usual. The cluster just becomes less robust if other nodes fail while the state store is offline. When the state store comes back online, it reestablishes communication with the other nodes and resumes its monitoring function. The Impala daemon, which is the core Impala component, and it is a daemon process that runs on each node of the cluster, is physically represented by the impalad process. It reads and writes to data files, accepts queries transmitted from the Impala shell command, Q, JDBC, or ODBC, parallelizes the queries and distributes work to other nodes in the Impala cluster, and transmits intermediate query results back to the central coordinator node. You can submit a query to the Impala daemon running on any node, and that node serves as a coordinator node for that query. The other nodes transmit partial results back to the coordinator, which constructs the final result set for a query. When running experiments with functionality through the Impala shell command, you might always connect to the same Impala daemon for convenience. For clusters running production workloads, you might load balance between the nodes by submitting each query to a different Impala daemon in round-robin style, using the JDBC or ODBC interfaces. The Impala daemons are in constant communication with the state store to confirm which nodes are healthy and can accept new work. Now that we understand the details of Impala, let's look at how it works with other components to function as an integrated ad hoc query system. There are clients, which are entities including Hue, ODBC clients, JDBC clients, and the Impala shell. These clients all interact with Impala. As shown in the previous slide, these interfaces are typically used to issue queries or complete administrative tasks such as connecting to Impala. There is the Hive Metastore, which stores information about the data available to Impala. For example, the Metastore lets Impala know what databases are available and what the structure of those databases is. There is the Cloudera Impala process running on data nodes, which coordinates and executes queries. Each instance of Impala can receive, plan, and coordinate queries from Impala clients. Queries are distributed among Impala nodes, and these nodes then act as workers, executing parallel query fragments. And finally, there's the distributed file system, HBase and HDFS, which work as storage for data to be queried. Here I will demonstrate how to run Impala from a virtual machine running CentOS. The first step is to download the Cloudera Quick Start VM from Cloudera's website. These virtual machines are available in VMware, VirtualBox, and KVM flavors. A 64-bit host operating system is required for all of these virtual machines. The Cloudera Quick Start VM already has the following installed: CentOS 6.2, CDH 4.2, Cloudera Manager 4.5.2, and Cloudera Impala 1.0. The next step is to open the virtual machine with VMware Player. Open a terminal and proceed to create some tables in HDFS. In the terminal at the prompt, create a new user directory and set the permission to world executable and readable. The user directory is located under the folder /user/myuser. The new table to be created is in the subfolder mytable. Next, we define a database named TPCDS. This database will have two tables named customer and customer address. Using a text editor such as gedit, create a script file and save this text as customer_setup.sql. This file defines the data types of each attribute in the two tables. A convenient way to set up data for Impala to access is to use an external table, where the data already exists in an HDFS file system, and one simply points the Impala table at that file. For example, we could run any SQL file in Impala shell with contents similar to the code shown on the screen. The data physically resides in HDFS directory tree under the directory named Hive, although this particular data is entirely managed by Impala rather than Hive. When we create an external table, we specify the directory containing one or more data files, and Impala queries the combined content of all the files inside that directory. Now we run the script. Initially, when we run the script in the virtual machine, we might see a permission error. In Impala shell, we need to set the permissions for the directory. After we set the permissions, we can run the script again. We now see that the script successfully finished running in Impala. Now let's query the data contained in the tables. Impala coordinates the query execution across a single node or multiple nodes depending on the configuration. We can execute queries on Impala by using the Impala shell command in interactive mode, passing a set of commands contained in a file, or by passing a single command to the Impala shell command. The query is executed, the results are returned, and the shell exits. Using the show keyword, we can display the attributes of a database in the terminal. The use keyword tells Impala which database to look for, and the show keyword displays all tables in the indicated database. We can use the describe keyword to look at the attributes of a table. We can examine the contents of a table in Impala. Because Impala often deals with tables containing millions or billions of rows, when examining tables of unknown size, be sure to include the limit clause to avoid large amounts of unnecessary output. If your interactive query starts displaying an unexpected volume of data, press Ctrl+C in Impala shell to cancel the query. Now that we can run the example database and query from it, we can create and populate our own databases. We can perform subquery, aggregate, and joins, insert data into tables, and perform all the other functions familiar in a traditional relational database management system. Thank you for listening to this presentation.